Welcome everyone. Welcome to another part of our series on video tutorials. We are looking at analog electronics right now, and the topic that we will be covering is transistor. We have already done three different topics in this part, that is semiconductors, PN junction, and rectifiers. The links to those video tutorials are given in the description below. Now, what is a transistor? Generally, when we think of a transistor, this is the picture that comes into our mind. Now, this is basically a portable radio which converts the radio waves into electrical signals and the electrical signals into sound waves. The transistor is basically a component which helps to amplify the electrical signal. The transistors actually look like these. These are some of the type of transistors. The video tutorial from now on will be on these transistors and not the one that we saw earlier. The transistors have other varied applications as well. This was one of the applications. Let's see what a transistor is. The transistors were first invented by Bardeen and Bratton in 1948, but it was William Shockley's invention in 1951 which replaced the bulky vacuum diodes in the amplifiers. Transistors are basically semiconductor devices consisting of the three regions separated by two PN junctions. Now, transistors can be manufactured using grown junction method, alloy junction method, zone refining method, beam led method, diffusion method, ion implantation method, to name a few. The methods won't be discussed in this tutorial. I recommend you to study books on semiconductor fabrication techniques if you are interested in the topic. Now, the transistor has three parts. We'll start at the center. At the center is the base. It is a very thin layer of about 0.0025 centimeter and forms the central region of the transistor, and it is lightly doped. This region has the polarity different from the other two regions. The emitter and the collector have the same polarities. The emitters are heavily doped and supply the majority carriers, while collectors collect the charges from its junction with the base and are therefore moderately doped. Ohmic contacts are made to these layers to transfer current. As this kind of a transistor has two junctions and has two different polarities of charge carriers. For example, the emitter might be of N type, hence the collector will be also of N type, so the base will be of P type. Because of these two polarities, the transistor is also called as the bipolar junction transistor. Before we move forward, it is noteworthy to say that this invention of Shockley gave him the Nobel Prize in Physics in 1956. Now, for normal working of a transistor, the emitter base junction should be forward biased so that the charge carriers can be injected into the base, and the base collector junction has to be reverse biased to accept the charge carriers in the collector region. Forward bias of emitter base junction creates a low resistance in the emitter circuit, while the reverse bias of the collector junction creates a high resistance in the collector circuit. So we have two different resistance regions, one low resistance region and one high resistance region. This two type of resistance region has actually given the name to this device, transistor. Transistor basically means transfer resistor. That is a device which transfers charge carriers from a low resistance region to a high resistance region. As we discussed, NPN transistor. The other type of transistor is the PNP transistor. Let's look into them. An NPN transistor is a transistor in which a p-type semiconductor, which is lightly doped, the base, is sandwiched between two heavily doped n-types. In PNP, the lightly doped n-type semiconductor is sandwiched between two heavily doped p-types. The symbol for an NPN transistor is on the top right corner, and the symbol for a PNP transistor is in the bottom right corner. It has to be remembered that the arrowhead is always on the emitter and the arrow is always from P to N. Now let's look into the operation of the NPN and the PNP transistor. First we will look into the NPN transistor. From the left to right, the first N is the emitter, the second P is the base, and the third N is the collector. They are denoted by the letters E, B and C respectively. The emitter is heavily doped, the P base is lightly doped, and the N collector is moderately doped. The emitter base junction is forward biased by the VEE battery, and the collector base junction is reverse biased by the VCC battery. The potential at emitter base junction is reduced, thus facilitating flow of electrons from the heavily doped emitter into the lightly doped p-type base. The reverse biased collector base junction draws most of the electrons into the collector terminal. As the emitter base junction is forward biased, the potential barrier at the junction gets reduced and electrons diffuse across the junction from the emitter to the base region. The holes diffuse from the base to the emitter region. In a transistor, the base region is doped lightly and holes are lesser in that region. Therefore, the hole diffusion current is less than that of the electron diffusion current. The total current consists of the hole current and the electron current, but practically it is just the electron current flowing from the emitter to the base. This electron current constitutes the emitter current IE. The base current is given as IB. The direction of the currents are as shown in the figure. As a result, the concentration of the electrons near the emitter base junction increases considerably. The reverse bias across the base collector junction causes drift of minority carriers. Holes from the collector region move into the base region and electrons from the base region flows into the collector region. The reverse bias creates an electric field which accelerates the electrons and sweeps them into the collector region. As a result, the concentration of the electrons near the collector base junction decreases considerably. The electron may recombine with the holes in the base and cause a large base current, but as the p-type base is not heavily doped, there are not a sufficient amount of hole present over there. Hence, the recombination rate is very low and the base current is practically very small. As there is a large concentration gradient in the base region, that is, it is having a large number of electrons as compared to the number of holes present there, the electrons swiftly diffuse towards the collector side, causing the collector current IC, which is nearly equal to the emitter current IE. The direction of the collector current is as shown in the figure. Hence, we can conclude that in case of an NPN transistor, the emitter current is the sum of the base current and the collector current. Now let's move on to the next type of transistor, that is PNP transistor. In case of a PNP transistor, from left to right, it has a p-type heavily doped emitter, n-type lightly doped base, and p-type moderately doped collector. The emitter base junction is forward biased by the VEE battery and the collector base junction is reverse biased by the VCC battery. The potential at emitter base junction is reduced, facilitating flow of holes from the heavily doped emitter into the lightly doped n-type base. The reverse biased collector base junction draws most of the holes into the collector terminal. As the emitter base junction is forward biased, the potential barrier at the junction gets reduced and holes diffuse from the junction from emitter to the base region, and the electrons diffuse from the base to the emitter region. In a transistor, the base is lightly doped, and in this case it is an n-type semiconductor, and hence the number of electrons is lesser in that region. Therefore, electron diffusion current is less than the hole diffusion current. As we have seen in the case of NPN transistor, the total current here is practically due to holes, the majority charge carriers only. It constitutes the emitter current IE. The base current is IB. Direction of both the currents are as shown in the figure. As a result, the concentration of holes near the emitter base junction increases considerably. The reverse bias across the base collector junction causes the drift of minority carriers. Electrons from the collector region move into the base region, and holes from the base region flows into the collector region. The reverse bias creates an electric field which accelerates the holes and sweeps them into the collector region. As a result, the concentration of holes near the collector base junction decreases considerably. The holes may recombine with the electrons in the base and cause a large base current, but again there are not many electrons available there, and hence the base current is practically very small. As there is a large concentration gradient in the base region, the holes swiftly diffuse towards the collector, causing a collector current IC, which is nearly equal to the emitter current IE. So again we can put forward the equation that we give in case of the NPN transistor, that emitter current IE is equal to the sum of the base current IB and the collector current IC. In the next tutorial, we will look into two kinds of transistor configuration, that is the common base mode and the common emitter mode. Till then, thank you.